Hi, today we've got a package from JLCPCB and it's quite a big one this time, so let's take a look inside. And so we've got some PCBs, some tape to hold down the stencils when you're applying the solder paste, and a couple of stencils for the assembly. Right, so what these are the motherboards for the lighting controller project. I've got 10 of these, so I've got plenty to be going on with, so I can control things all over the house. And you can see it vaguely represents the original drawing that I did in one of the early videos. So the idea is that you can have the various module PCBs. So far we've seen the relay boards and the constant current LED drivers. And these are designed to fit onto the PCB in these areas. So you can see they're labelled module 1, 2, 3 and 4. And you can mix and match the boards. They've got a identification pair of resistors so that the main board knows what's plugged in. And then you can mix and match depending on what room and what lighting you need to control. So we'll have a little look at the schematic for this board, but essentially what we've got is we've got a whole load of switch inputs so that you can turn the lights on and off and dim them up and down just with standard switches. We've then got there's a dip switch here which sets the board address because there's two interfaces here, two RS485 interfaces. One of them I've labelled local, so that would be for sensors that are in the room. So for example, if we end up implementing some microwave sensors to check whether there's occupancy in the room, those could be on some kind of RS485 bus, or even if there's some analog control, because all of these inputs are for switch contacts, not for potentiometers and that kind of thing. So we can have little nodes all around the room. And then we've got one that's labelled external, and that's probably going to be to link all of the main boards together. And then, we can connect it up to a Raspberry Pi or something like that and do some logging or some global control of all of the lights. We've got the DC input on the left-hand side and some DC to DC converters around here. And that's probably what we're going to look at today, powering these up and checking they're working, along with the switch inputs. And then what we've got is the modules with some multiplexing switches so that we can control different types of modules. We'll have a look in the schematic shortly at what that's all about. We've got the main microcontroller, which is a PIC24FJ microcontroller, and then some GPIO expanders for things like the 7-segment display, which just indicates status, some status LEDs, and a few other bits and bobs. So let's have a look at the schematic, and then we'll have a closer look at how it's been implemented on the PCB. Right, so we've actually got a few pages of schematic here, so I won't go into great detail, but essentially what we've got is a system that is designed to take an input of either 12 volts or 24 volts DC. So there's two DC to DC converters here, one supplying the 3.3 logic to the board, and one supplying the 12 volt for the PCB. And if it is supplied with a 12 volt supply, then we just simply won't fit the DC to DC converter, and we'll put a link across there so that the 12 volt input on the board is fed straight into the 12 volt logic on the PCB. But these two DC to DC converters are based around the Texas Instruments 54202, which are some relatively high efficiency DC to DC buck converters. And the high efficiency comes from partly the fact that it has a relatively high switching frequency of 500 kilohertz. That means you can use smaller inductors, so you get some of the reduced losses in that inductor because they're physically smaller, don't need so many windings, that kind of thing. But also these are synchronous DC to DC converters, so you might be wondering where the freewheeling diode is. It doesn't actually have one, it has a pair of MOSFETs, and instead of the freewheeling diode, a MOSFET is physically turned on during the off cycle of the PWM waveform, and that gets rid of the losses associated with the voltage drop across the freewheeling diode. So that's how you get some of the higher efficiency with these DC to DC converters. But they still have generally the same structure as normal, so our inductor into our bulk capacitors, and we've also got a feedback network here with a little bit of compensation to keep the loop stable. On this page of the schematic, we've got the switch inputs. So on each PCB, we can have a total of 12 different switches connected to the board. And because these are standard switches that can be used for mains use in the UK, I wanted to provide a little bit of protection against a high voltage being applied to the board. So what we've got is a Zener diode and fuse arrangement. And the idea is that if the input voltage exceeds 30 volts, we'll start to get current being conducted through the Zener diode, and then if the current is great enough, it will blow this 0603 fuse. Similarly, if an AC supply was connected, if we get a reverse voltage applied to this pin here, we'll get current being conducted through the diode this way, and then again, if there's enough current flowing, it will blow this fuse here. Then what we've got is a constant current arrangement, and this switch input can accept anywhere from about 9 volts up to 30 volts quite happily, and conduct the same amount of current through the LED. And what you have to remember is, with these opto-isolators, the LED is providing the base current to the transistor. So if you want this pull-up and transistor arrangement, so the open collector arrangement, to behave in the same way, no matter what the input voltage on the switch input here, you need to have a constant current through that LED so this behaves predictably. So we've got a constant current arrangement based on 2 transistors, and then the current is set by this 180 ohm resistor up here. Right, so the plan today will be first of all to power up the DC to DC converters. On a bigger PCB like this, it doesn't usually make sense just to populate the whole lot, because you might have made a mistake with the power supplies and then you might blast 24 volts into your electronics on the board. So we'll get the DC to DCs working first and just check that they work as expected. And then if we get time, we'll have a little look at these inputs on the switches just to check that those work properly. And then probably in the next video, what we'll do is assemble the rest of the board and get the firmware up and running. So one thing that I wanted to draw to your attention on this particular board is that for this one, I've gone for a 4-layer PCB. So because of the relatively constrained layout, so I wanted all of these switch inputs up here, then I wanted the modules to sit all next to each other, and then have all of the other electronics on the side here. The physical placement was somewhat constrained, which means that also the routing is somewhat constrained again, and that means that you can spend a lot of time optimizing the routing so that you can try and get it all in 2 layers, but you have to factor in the amount of time that takes and the compromises that are made. So what we've got on here is 4 layers where we've got signal layers, power layers, and that kind of thing. Everything is a lot simpler to do on the extra layers, and the incremental cost is relatively small compared to what it used to be. I can't remember the exact pricing on this board, but certainly more affordable than 4-layer PCBs ever used to be. So we've got our 4 layers. The actual board itself looks no different to a standard 2-layer board, but yeah, we've got those extra layers inside, and you can see on the bottom layer a lot of my tracers are top to bottom, and on this layer you can see a lot of my routing is left to right. So let's have a little look at the layout first of all. And here we go. So this is the layer that you could see, the top layer, and this is where we've got all of our left to right routing where possible. There's a few diagonal tracers up here because it makes sense to do that. And then we're flooded with a ground plane as well, so that that facilitates getting power to each of the ICs and that kind of thing really easily if you've got a ground flood or a power flood on the top layer. So here we've got the second layer, and similarly we've got mainly left to right routing here. There's a few tracers that go up as well, so to this 7-segment display, because there's no other tracers in this area, it makes sense just to use one continuous trace rather than dropping through to different layers all the time. And then we can also see we've got a flood here, power plane, and this is the 3.3 volt supply from the DC to DC converter. So the entire second layer flood is for the 3 volt supply. Then here we've got layer 3, and actually there's no routing on this layer. This is just a ground plane, and by having a ground plane separated by a 3.3 volt plane and then a ground plane again, we actually get really quite a good amount of capacitance between the layers, and we can probably measure that. In fact, we will do in a minute. Finally, we've got the bottom layer, and as you saw, this one generally had routing from top to bottom, and by separating the left to right and top to bottom as far as possible, it does simplify the layout process a lot more. Obviously, if you've got very specific routing requirements around things like DC to DC converters or analog circuitry, then obviously you prioritize those before going for general rules such as top to bottom and left to right. But it certainly simplifies the whole process. And again, we've got another ground plane on the bottom layer as well. I thought we'd just have a look to see how much capacitance you actually get on the board by having the 3.3 volt as a plane and then the ground plane on another layer. So we'll use a little peak meter here, and I'll place the probes across a capacitor that's on the 3.3 volt supply. And what you can see here is we're getting almost 1 nanofarad of capacitance on the PCB, just by the PCB material itself. So that capacitance is distributed over the entire surface of the PCB, which means actually we get really good transient response, really good bypassing of digital parts on the PCB. Obviously I've still gone for the standard capacitor next to each digital device, but the fact that we've got our distributed capacitance all over the PCB is really handy and means that our decoupling is going to be really excellent on this PCB. So today we're just going to assemble the PCB by hand with a soldering iron. Because we're only assembling a little bit of the PCB, it doesn't really make sense to waste solder paste in the nozzle on the syringe or to get out the hot air station. Sometimes it's just quicker to do it by hand, especially where there's only a little bit to assemble anyway. Right, so here we've got the minimal amount of components placed to have the 3.3 volt rail up and running. So this is a fairly optimized layout for the DC to DC converter. Once you reach the kind of 500 kilohertz region, you do need to pay attention to the layout quite closely. So we've got our input capacitor almost right up against the DC to DC converter IC, and the output ceramic capacitors are right next to the inductor and then connected directly onto the ground plane, so we've got really short loops. We've also got an electrolytic capacitor, but the placement of that one isn't quite so important because the ESR is a little bit higher than the ceramic capacitors, so it can be a little bit further away without too much trouble. And then we've got the feedback resistors right next to the feedback network on the IC. So this is the minimal amount of components that we need to test the 3.3 volt rail. So now we can apply power and have a look at what we're getting. Okay, so that's the wires connected up. So we'll now turn on the power supply. And that's a good start. So we've got a blue LED that's lit up here. That's on the 3.3 volt rail. And I can probe one of the capacitor placement parts on the side of the PCB. And we can see here we're getting 3.301 volts DC. So that's pretty much bang on. The next thing that we'll do is just check the waveform on the oscilloscope, and then we'll also test the DC to DC converter under load. Right, so hopefully you can see what's going on here. What we've got is the Fluke 28 measuring the voltage on the 3.3 volt rail. We've got the Fluke 87 measuring current, and then we've got the Rigol, which is AC coupled onto the 3.3 volt rail so that we can see the ripple. And I've had to turn off a lot of equipment in the lab because the probing that I've got here is not optimized, so actually it's picking up a lot of noise. Just with the lab lights on, we were seeing about 200 millivolts of noise on this waveform, so that was completely swamping out what is actually going on the board. But definitely the probing isn't optimal, so we're going to see a little bit more noise than what's actually happening on the PCB. In terms of a DC load, I've just got a MOSFET with an op-amp and a potentiometer, just so that we can draw some current from the PCB. So if we now increase the current that's being drawn, so here we've got 100 milliamps, which is approximately the maximum that I'm expecting to see on this PCB, and that's sort of what the component choice has somewhat been optimized for. So we've got 100 milliamps being drawn, the voltage is still bang on 3.3 volts, and we're just seeing a little bit of noise here on the AC waveform. So what we're actually seeing is we're seeing a little switching spike, which actually is probably most likely not there. It's just that it's being picked up by the lousy connections that I've got going on here. And then we'll see a little bit of an increase in the voltage just here, and then it starts to decay again. And the way that these DC to DC converters work is the output voltage is compared against an internal reference. So when it's below the reference, it turns on the transistor to start charging up the capacitor. Then once it goes past a threshold, it then turns off the transistor and we see a little bit of discharge. So we're always going to see some ripple, and the peak to peak I think here is not actually that real. I think that's just picked up by the wiring here. So at 100 milliamps what we're seeing is about 160 millivolts average noise on the supply line. There we go. So that's about half an amp being drawn. And you can see that the noise is increased somewhat. We're still seeing the spikes which are just generated by the switching event, and you can see slightly more pronounced is the charge and discharge cycle of the waveform. But that looks completely as I would have expected. We're still getting a good 3.3 volt rail on the PCB, and we don't seem to be having any troubles here. And finally, we can just work out how efficient this design is. So that comes out at about 80% efficiency, because we've got 23 volts going in, 88 milliamps, that's 2 watts going in. 3.3 volts at 0.496 amps is about 1.63 watts, and the efficiency therefore comes out at 80%. However, I don't think that number's quite correct, because if we get the infrared thermometer and press it right up against the PCB over those components, the highest temperature we got there is about 32.5 degrees. So if it was 80% efficient and we're putting 2 watts in, we would expect about 400 milliwatts of power dissipation on here, and we'd certainly see a temperature rise of more than a few degrees. So actually what we're seeing is some inefficiencies introduced by the test setup that we've got. So we've got the shunt resistor in the Fluke 87. That will be dissipating some power, so we're losing some power in there. We've also got about 2 meters of very thin wire between it and the DC load. So if I probe at the DC load, we're actually getting about 3 volts at that point. So we're seeing 0.3 volt drop, which is about 150 milliwatts on each wire. So that probably comes out closer to 90% efficiency. So I'm quite happy with how that's behaving. So next we can build up the 12 volt, just check that that works, and then that's the power supply section sorted. Okay, and now the 12 volt DC to DC converter is all in place. We're getting about 12 volts. The schematic noted that we needed a 100k and a 5.2k resistor divider to get 12 volts exactly. Obviously 5.2k isn't a standard value, so I've gone with 5.1, which has resulted in a very slightly higher voltage. But the 12 volt isn't used for anything in particular on the board that's sensitive, so that's completely fine. Right, so I did just want to talk about how the modules plug into the PCB, because what we've got on these modules is a 10-way pin header and a screw, and a few people mentioned that the screw was not in a great place for the connector block. Unfortunately, that's about the only place that we've got, just based on the layout, because the idea is that we have this female 10-pin socket which will be soldered into the main PCB, and then we've got a nylon spacer as well which is screwed into the main board. So there's screws on this side holding that spacer in place, and when that's soldered into place, you'll be able to just select your module, plug it in, and then you can screw a nylon screw into the spacer like this. And then that holds the board in place, so you've got mechanical fixing here with the screw at the end that's probably going to see the most strain, and then at this end you've got the pin header which will be soldered in obviously, and that will hold this other end of the board in. So you can see if I put the screw anywhere else, we probably wouldn't get the mechanical fixing where it's most needed. And then what you end up with is about 12 millimeters of gap between the PCB and the module, which is enough to provide a decent amount of clearance. So considering that some of these relays and other modules are going to be running at mains, that's plenty of clearance between the module and the PCB. So I think that works quite nicely. There was a question also, which is quite interesting, about having one of the mains powered modules sitting over the microcontroller, and that's probably a valid concern, something I've not really considered. On the relay modules, it's probably where it's the most prominent, because you've got switch contacts, and if you're switching an inductive load, you may well get an arc or spark event on the contacts when you open or close the relay, which could be enough to disrupt the electronics. So really I should have put a snubber network on here so that the arcs are suppressed. On the dimmer module it shouldn't be so much of a problem. We've got some control over how the waveform is switched, and so I'm not expecting that to be an issue, but yeah, it's a valid concern for things like the relay. But overall I think that works quite well, so that's going to be how that works. And obviously any module that you plug in is going to be of the same design, so you can plug it in and no problem. In terms of clearance, you can actually see that the terminal blocks are in line with the top of the screw, so putting in your wire into here is not going to foul on the screw, so it's not actually going to cause any obstruction. It actually works quite nicely. Right, so fast forwarding a little bit, I've populated up some of the board now. So I've done all of the switch inputs at the top there. So there's a few components on the top side for each switch, and also a few, so the Zenodiode and that kind of thing on the other side. But I thought we'd just have a little look at the circuit in LT-Spice just to see what's going on with these switch inputs. Right, so here we have a schematic which represents somewhat what's going on the PCB. The bit of interest is the LED driver circuit. So what I wanted from this was to be able to have a relatively wide input voltage range on those switch inputs, and for it to behave in the same way no matter what that voltage was. So we've got this constant current LED driver based around 2 PNP transistors, and I have explained this circuit before in another video, so if you haven't watched my video on constant current LED drivers, I highly recommend that you take a look at that, so I'll put the link above here. And what this is it's a constant current driver circuit using the property of the transistor at the top here. So the voltage drop between the base and emitter, which is somewhere in the region of 0.6 volts. It's not a tightly controlled parameter, so this isn't a perfect constant current driver, but it's not needed for this application. But using that property of around 0.6 volts, along with this resistor, gives us a current of about 4 milliamps through this LED. So what we've done is I've set up a sine wave on the side here, which sweeps the voltage between 0 and 36 volts to represent sort of the edge parameters of what could go on the board. And if we run the simulation, we can see that we've got our sine wave coming in here, so 0 to 36 volts. And if we have a look at our LED, it's turning on at about 8 volts here. And the reason it's turning on at 8 volts is because I also have a Zenodiode at the bottom here to set the threshold at which the LED turns on, just so that the circuit isn't susceptible to capacitively coupled currents in the house wiring. So it gives a little bit more immunity to the design. What we're actually seeing is that once it goes above 30 volts, this Zenodiode is starting to clip. So if we have a look at the waveform here, you can see actually it started clipping the waveform around here. And as you saw in my schematic, we had a fuse. And if we look at the current through that, once that Zenodiode starts conducting, we see a big current of about 1.6 amps, which would be enough to blow the fuse on the PCB, so protecting the electronics. But other than that, you can see that the LED works perfectly fine from about 8 volts input all the way up to 30 volts. Right, so I thought we'd now test the circuit on the PCB, and in the schematic we've also got this additional resistor just here, and that is designed to draw about 8 milliamps at 24 volts, and that is so that we have enough current flowing through the switch so that it exceeds what's known as the wetting current of the switch. So if you use a switch for particularly low currents, what can happen is an oxide layer can form on the switch contacts, and then over time the switch will become very high resistance and fail prematurely. A lot of switches, depending on the coating material, will need a certain amount of current to flow through the switch every time that the switch is opened and closed, so that the oxide layer doesn't form or so that it's broken down. So we've got a little bit of extra current flowing through this resistor, and then we've got our roughly 4 milliamps that's designed to flow through the constant current LED driver circuit. So I thought what we'd do is we've got a Fluke 87 here, which is set up to measure current. And I thought we'd use that to short out the switch contacts, so representing the switch. And then we've got the Fluke 28, which we can use to look at the voltage at this node here on the schematic, which is the input to the microcontroller. So this has a pull-up resistor, which means that when the switch is open, we'll normally see this voltage at 3.3 volts. And then when the switch is closed, we should see that this drops very close to 0 volts. We'll just see sort of the voltage drop across the transistor here. So let's power up the PCB. And if we probe the point here, we're seeing about 3.3 volts. So that's exactly what we expect. And then if I try and short out the switch contacts, we can see we're getting about 12 milliamps flowing through it, and the voltage at the output here has dropped to basically 0 volts. So that's the voltage drop across that transistor. So that all seems to be working as far as all of the components that I've got on the PCB. So I'm quite happy with where we've got to. In the next video, what we'll do is put the rest of the parts on the PCB and then we can put some firmware on the microcontroller and plug in some of the modules and see how they work. We've also got the dimmer module to solder up. I'll do that once this board is fully assembled, because we do need this all working before we can test that it's behaving as expected. But I'm fairly happy with how that's looking. It's certainly seems to be behaving exactly as expected at this moment in time. So unless there's any surprises with the rest of the circuitry, I think we're in a fairly good position. So thank you to JLCPCB for providing these 4-layer PCBs for this project. As you can see, it's made the layout really quite nice. And for anyone who is near the Rome area, JLCPCB are going to be attending the Maker Faire in Rome on the 18th to the 20th of October. So if you happen to be able to visit that, there will be some popular YouTubers at the JLCPCB stand. But also if you visit, you'll be able to get some coupons and there'll be some giveaways as well. So hopefully you found this video useful, and until next time, thanks for watching.